Welcome back to Physics 151 Online. Today I'd like to give a brief introduction to non-constant acceleration in 2 and 3 dimensions, and then finish with an introduction into acceleration in circular motion problems. So first, if the acceleration of an object that's moving in 2 or 3 dimensions is changing, if any one of its components is changing so that it's not constant in time, then we have to directly use calculus in solving problems about its motion. So just to summarize, using equations that you've seen before, but just to gather them together into one place, we can remember that when we take the definition of acceleration as dv dt and cross-multiply that equation and then integrate both sides, we get the following general result. The change in the velocity vector is equal to the integral of the acceleration vector between time 0 and the final time. Now, that implies, when we've got a two-dimensional problem, that you actually have two equations arising from this, one for the x direction velocity and one for the velocity in the y direction. So here are the two equations. So this vector equation, we very rarely use this directly. We usually break it apart into its components. And so we have two nearly identical equations, the only difference being the component. The same kind of thing holds true for position, because then if we use the definition of velocity as the derivative of position with respect to time and integrate both sides of that equation, we get that the position change is equal to the integral of the velocity vector between time 0 and a final time t. This, of course, has two equations that describe the components for the x direction and the y direction. And so the general procedure in treating a problem where the acceleration is not constant is first, on the left-hand side of this slide, to use the acceleration, integrate it in the x and y direction in order to find expressions for the x and y components of the velocity. Those could still be functions of time, and if they are, then use those in order to perform the integral necessary to find expressions for the position x and y as a function of t. And I've just used equations here reflecting the case of two-dimensional motion. If you had a third dimension involved, then of course you would have equations for v sub z and also for the component z. So we'll do some examples of this in class, but that's the basic procedure for handling motion problems for objects where the acceleration changes with time. Alright, now just a few minutes then to introduce the special expression that we get for acceleration in a problem involving circular motion. So let's just assume that we've got an object moving in circular motion, and perhaps this could be a car on a racetrack, or a car that's even moving in a portion of a circular path, such as when you get off the exit ramp off an interstate and you're going around in roughly a circular path. So if a particle with mass m has a constant speed in a circular path of radius r, then what can we deduce from that kind of motion? And so what we want to do is consider the velocities of that particle at some initial location and then its velocity vector a short time later at this final location. We're going to ultimately take the limit where these two instants in time are very close together, but for the purpose of the diagram I've drawn them as if the object travels quite a ways around the circular path. So those two vectors, velocity initial and velocity final, can be related to a couple of geometrical parameters. One would be the angle, delta theta, which tells you the portion of the angle associated with that circular arc. Then delta s would be the displacement of the object from the final to the initial position, and finally r being the radius of the circular path. And they're simple relationships that just depend on geometry that we're all familiar with that allow us to relate these quantities. So first what we're going to do is draw a triangular diagram where we draw the we draw the final vector, v final, right? We just pick that vector up and bring it over here, and then we take v initial, but we take the negative of that vector and draw it over here. And the reason for doing this is that allows us to construct the change in the velocity vector. Remember, change is final minus initial. And so as a result, what we see is v final plus a negative v initial gives us this delta v. And notice, if I draw the diagram carefully, that this delta v points downward in this diagram, which would be toward the center of the circular path. And if you take those 2 points where the v initial and the v final are drawn and bring them very close together, you will always see that that change in velocity is directed towards the center of the circle. And then of course the delta theta angle, if again I draw this sketch very carefully, the delta theta angle is on the right hand side of this triangle. Now these 2 triangles, the one with the dotted line and then the one with the velocity vectors, are similar to each other because they have the same angle involved in them, and then sides that are related in the same way. The magnitudes v final and v initial, if this object has a constant speed, they're the same, just as the 2 sides in this triangle both reflect the radius of the circular path, and those are both the same. And so we can replace in our equations, we can replace the magnitudes of those 2 vectors just with the symbol v. And remember, that's what v means. V without a vector sign is the magnitude of the velocity, which is otherwise called the speed. And so since those triangles are similar, what we can do is make a ratio between the side opposite the angle, which over on the left is delta s, and then the radius of the path, which is the leg of one of the triangles, and that ratio, delta s over r, is equal to, in the right-hand triangle, the side opposite the angle, which is the delta v, divided by the other leg of that triangle, which would be v. So delta s over r in the left-hand triangle is equal to delta v over v. Alright, so let's start on the next slide at that starting point. What we do with that is solve for delta v. So then delta v is equal to v delta s over r. And what we will now do is divide both sides of this equation by a time interval delta t, so that we'll get how the velocity is changing as a function of time. So if we just divide both sides by delta t, delta v over t is equal to v over r times delta s over delta t. And these deltas are just changes. But what we want to do now, in order to get the instantaneous change, is to take the limit of the left-hand side where the time interval delta t becomes very small. And so that, if you look at the right-hand side over here, the v and the r are constants, right? So that v over r come outside, and we're taking the limit of delta s over delta t, where delta t goes to 0. It becomes very small. So on the left-hand side, what we have is an acceleration, an instantaneous acceleration. What's special about it is we already know the direction. It's always directed towards the center of the circle. On the right-hand side, delta s over delta t, well, that's going to be the speed, right? Because it's the change in position with respect to a change in time as the object moves around the circle. And so what we have on the left-hand side is what we call the radial acceleration, a radial. On the right-hand side, if this limiting term gives us v, then we have v squared over r. And this becomes what is probably to many of you a familiar equation for an object in circular motion. Strictly, this would be for uniform circular motion, where the speed v stays constant while the object is traveling around a path of radius r, but it also turns out to be correct even if the speed is changing. As long as the radius is the same, the acceleration directed towards the center of the circle is always equal to the object's speed squared over that radial distance. And there's just one additional thing to say. For uniform circular motion, the speed would stay constant, but if the object is speeding up or slowing down, then there's another component to its acceleration, and that would be what's called the tangential acceleration. So the magnitude here of the velocity vector, if that being the speed, if that's changing, then there's an additional acceleration along the tangent to the path. And so there's a radial component, and then there's a tangential component for the most general case. And I'll just say in closing, it might be a little bit strange if you think about an object that has a constant speed as it goes around the circle. It might seem strange that there's acceleration. And why is there acceleration? The object's not changing its speed. But remember, velocity is a vector. And since acceleration as a vector is the derivative of the velocity vector, if the velocity vector is changing its direction, there must be acceleration happening, even if the magnitude of the velocity is not changing. And so that's how we know that circular motion inherently involves acceleration, because as the object goes around the circle, its direction is constantly changing. If the magnitude changes too, then we have the case of non-uniform circular motion, where there's also this tangential acceleration. So I hope this is a helpful introduction, and I will see you in class.